Okay, thank you very much. I am assuming that now you can see the shared screen.
Yes.
Okay, thank you. Okay, so I will also try to be very fast because this is essentially what is the last session is dividing you from the break and from the buffet. So I guess you want to know about the research, but you also would like to go and hit and discuss a little bit among yourself. So I will be very fast. This is the short presentation of the Intelligent System Lab. So we are deeply focused in AI. With respect to the different topics that have been discussed up to now, we are focusing more on decision making, which is essentially amounts to how to design agents that can interact in the world, so take decision, so that you can sense from the environment, plan what you want to do, and then actually act, see how this changes the world where the agent is operating, and restart the cycle. This is the core cycle of AI. And this is what we focus on the most. The main research topics related to this, probably one of the most important is reinforcement learning, and in particular deep reinforcement learning, which is when you do reinforcement learning using deep neural network, which is obviously strongly related with machine learning. But it's a bit from, it takes this from a different perspective. This is mostly related with the control of the agent. So what you're trying to do with reinforcement learning is not only to extract information from the world, but actually to be able to have an agent interact with the world and know and to learn, so to adapt its actions based on the a reward signal that is coming from the world. This is very important when you don't know how to exactly model the world. So if you don't have a model of the world and you want to build this model or adapt this model, reinforcement learning is the way to go. Reinforcement learning is a very important topic in modern AI, and this can be applied to several types of agents. So what we really care about in the ISLa lab is mostly the methodological parts, and then this can be applied to several different applications that I will briefly describe. So this can be applied to simulated agents. You can see, for example, here an example of this, real robots, or cyber physical systems, such as, for example, in intelligent buildings and so on. But what we really care about is the methodology. So reinforcement learning is one. We have planning and high-level control, which is mostly related with what you can do when you actually have a model of the environment and you want to use this model to take the best action and be more effective. Another topic which is really important is anomaly detection and forecasting. And in particular, in this case, what we are focusing on is how to detect anomaly in the behavior of an intelligent agent, rather than, for example, a faulty census. Things like, for example, you can see in this figure here where this boat was performing a path, but it was always shifting a little bit to the right. Okay, this is not wrong. The path was completed, but it's strange. It's an anomaly that you need to detect. And of course, using AI technique is key for detecting this type of anomaly. Then we focus significantly also on the coordination of multi-agent system in general, and in particular for multi-robot. So instead of going into some details of all these elements, I will just show you a couple of videos of systems that we developed and that are actually working. And what you can see here is an example of a multi-robot coordination problem. In this case, this is applied in an industrial scenario, and you can see that these are two mobile robots that needs to pick up objects. So you can see the human operator, which in this case was also the developer of the system, Antonello, was placing packages on top of the robots, and then the robot will move to a different station where another human operator will pick the objects. What you can see now is really interesting because one of the two robots is moving far from the delivery point to make room for the other robot. This is a very important and interesting behavior because this requires a high level of coordination between the two platforms. That is exactly what we work on. So our work here is mostly on how you program this robot in a way so that for different environments, they will be able to show coordinated behavior. The other example that I would like to show to you is related to reinforcement learning, but in particular here, the interesting part is the first word, so safe reinforcement learning. This is a huge topic in AI, and is related to the concept of being able to develop agents that can interact in the world, okay, but also maintain some level of safety, okay? So in this case, what you see is an example that has been developed in a simulated environment, but is following, as you can probably see, the application of the water drones that has been discussed several times. In this case, you can see that we simulated, and this is, by the way, is Unity, so it's a game engine that is used more and more in the robotics community and in research in general. We simulated a situation of the world with obstacles and waves, and you can see, and essentially what we did was using a deep reinforcement learning approach to make sure that our vehicle can actually reach the target, which is the red ball. This is after training, and in particular, in this case, what you have seen was the boat being able to reach the target after the training in a scenario that has never been seen by the boat before. So this means that the reinforcement learning algorithm was able to generalize. Okay, this is very interesting and is sort of the edge of the research today. But what is really our focus in this case is the safety part, which is what I will try to explain now. Essentially, since this is based on deep reinforcement learning, so on a deep neural network, it's very difficult to understand what the network will do with respect to different inputs. And in practice, it's impossible to guarantee that the network will never, so the boat will never hit an obstacle, so that the network will never take a wrong action. So our idea here is to provide formal guarantees, which is more, so it's different than just saying 95% of the time the network will succeed, but formal guarantees on specific properties. Okay, so we give a high-level property. In this case, the property was something like, if there is an obstacle close to the right, you should never turn right. What you can see here is the training model that actually makes a mistake that was never seen in the training part. But now with our violation, with our approach to guarantee that violation can be avoided, this is recognized by the system and avoided. And so we can give some flavor of guarantees to the safety, which is really important, especially in safety critical applications. So as I said, I will go very quick, so I won't go into more detail on this. Of course, if you're interested, you're more than welcome to contact me or the group that that work together with me on these topics. Let me briefly explain the link with the degree that we are presenting, and this is of course very strong and is related to the 4 main courses. So the 4 mandatory courses: machine learning and deep learning, of course, as you can imagine, but also planning and automated reasoning, which is more related to the symbolic part of AI, reinforcement learning, obviously, and advanced programming, and then also explainable AI, because much of the activity that we do for the anomaly detection is actually related to this part. We then have obviously a strong link with statistical learning and knowledge representation, and clearly with AI and robotics, because as you've seen, most of the methodology that we develop are then focused towards robotic scenarios. This is all for what concerns the ISLa lab. This is the current composition of the group, and we really hope to have you on board soon for project, stage, thesis, or just collaborations on these topics. Thank you very much.